Welcome to today's central exercise class. As usual, we'll be happy to take your questions in our live chat. The chat is available here at chat.tum.de. And then please use this channel here, MA9714-CE, to post your questions, and we'll try to answer them either in the chat or here live on air. As usual, the chat will be moderated. Today's moderator is Kyoyoi. Kyoyoi, would you introduce yourself quickly for those who haven't met you yet?
Hello everyone. So I am Kyu Hyu, and I am working at the mathematics department. So I'm here today to monitor the chat channel. So please feel free to ask your questions in the chat. So.
Okay, let's start with sheet 8 right away. So on sheet 8, we have two problems for the central exercise classes. Both deal with optimization under certain constraints. So in the first case, we have this function here to optimize over a set C that is given like this here. And in the other case, we have a set F given like that. And again, we have some function to optimize over F. In both cases, we'll minimize because that's what we discussed in the lecture explicitly. But of course, it shouldn't be hard to adapt that to maximization problems. So if you want to give that a try, feel free to do so. Let's start with C81. And as you can see, the feasible set here is this set C, a circle. So basically what that says is we measure the distance, the norm, of this difference. So the distance between a point X and the point 1, 0, and the distance needs to be 3. So what we have here is the set of all points that have a distance of 3 from this point 1, 0. And that, of course, is a circle around that point 1, 0. So that's the first thing that we should state here. Of course, formally, you don't have to know that to solve the problem, but it always helps to have some intuitive understanding of what's going on. Right, so that's set C here. That is the set of all points that have a distance of 3 from the point 1, 0. And that means C is a circle of radius 3 centered at that point 1, 0. So that's the set that we're optimizing over. And then we have this function here, f of x1, x2, given us 2x1 plus x2, and we want to minimize that over C. Okay, so we have a constraint optimization problem, and if you have a problem like that, you usually first reformulate it to be in a certain form that we need for our formula to work. And that is minimize an objective function subject to constraints that have a right-hand side of 0. And that could either be equality constraints or less or equal to constraints. So in this case, that form would be, we want to minimize the function f given as 2x1 plus x2. And we want to minimize that function subject to the following set of constraints. And in this case, we only have one constraint, and that is expressed as a function that we call h. That also depends on two variables, and that is the constraint function that we have here, which expresses basically this distance constraint here. And what that means is we have the function x, well, let's write like x1, x2, like a vector x1, x2, minus 1, 0, minus 3, is 0. So we just reformulate that to have a right-hand side of 0. And of course, we can also write that norm explicitly. That would be a square root. And it usually helps to avoid square roots. It makes the expressions a little nicer. So in this case, we can easily just take the square of that function. So we can take the power 2 of that, and then also of that. Because if the norm is 3, then of course the squared norm is 9. So 3 to the power of 2, and that's the same, right? Norm is positive anyway, or non-negative anyway, so we don't have to take care of signs in this case. So we could also reformulate that as minimize f, which is 2x1 plus x2, subject to h, which is, well, if we write that norm explicitly, what that is we have x1 minus 1 squared plus x2 minus 0 squared. So that is x1 minus 1 squared plus x2 squared minus 9 equals 0. And that here just look a little nicer than the expression with the square roots. But of course, you could also solve the problem with the square roots that work pretty much the same way, just may not look that nice. Okay, so what do we do here? If that is the problem that we have, basically we can apply the method of Koresh-Kuhn-Tucker. Basically, that says we need to find the KKT point of that. And the KKT point is characterized by a set of constraints. So the candidate points for minima over constraints, equality or inequality constraints, are always KKT points. So we're going to find all KKT points and then see which, if any, of those is a minimum. So we want to find the KKT points as candidate points for minima. And to do that, we need to satisfy the KKT conditions. Basically, for equality constraints, there's only 2 conditions that we need to satisfy. Of course, the equality constraints themselves need to be satisfied. And we have this Lagrange equation that needs to be satisfied. And that says the gradient of the objective function f plus the Jacobian of h transposed times a multiplier, we call that c, needs to be 0. So that's the Lagrange function, or the Lagrange condition. So what we need to compute is we need to compute the gradient of f and the Jacobian of h. Okay, so let's do that. Gradient of f. Well, this is the function f here. So the partial derivative with respect to x1 is just 2. And the partial derivative with respect to x2 is 1. So that function has a constant gradient, the vector 2, 1. And for the Jacobian, so the Jacobian of h at the point x1, x2. Again, we want to compute the partial derivatives of that. So the partial derivative of this function here with respect to x1, x1 only appears here. So that is given by 2 x1 minus 1. And the partial derivative with respect to x2, x2 only appears here. So that partial derivative would be 2x2. And remember, for the Jacobian, we have 1 column per variable or per partial derivative. and 1 row per component. This function only has 1 component here, this one. So we only have 1 row. We have 2 columns. Basically, again, the gradient of a real valued function is the transpose Jacobian, right? Okay, so here's our Jacobian. And now we can write down the KKT conditions for this setting here. And again, those KKT conditions, this here, we need this Lagrange equality here. So we have 2, 1. This is the gradient of f. Plus, then we have the transposed Jacobian of h. So instead of columns, we now have rows. We transpose that. So we get 2 x1 minus 1 and 2x2. And then we have this multiplier here. And there's 1 multiplier per constraint. And in this case, we only have 1 constraint, so it's 1 real value multiplier. So we only get 1 multiplier, that's our C. So this here is the Jacobian transposed, and this is the real valued multiplier, and that is just a real number, right? And part of the equations we need to solve, right? So we now have equations in x1, x2, and in the multiplier C. And the right-hand side of this is the 0 vector. So this is the Lagrange condition. And as I said, we only have equality constraints. So the only other condition that we need is that these equality constraints be satisfied. And that simply means we need to take this equation here and we need to satisfy that. So the other KKT condition that we have is x1 minus 1 squared plus x2 squared minus 9 equals 0. So what we end up with here is a system of 3 equations. Right? Here's one. Here's the second one. And here's the third one. And the variables are x1, x2, and c. So basically what we have to do is we have to find all possible solutions of this equation system. And then those are our KKT points, our candidate points. And among those, we'll hopefully find the minimum that we want to find. Before we go on solving the system, are there any questions up to this point?
I think there is no questions at this point.
No questions at this point. Okay, wonderful. So basically all the rest is just some manual labor. We just need to go on and solve that system. What you often try to do is you often try to solve these first equations here for x1 and x2, if that's possible, and then substitute that into the third one. So you get an equation that only contains 1 more variable, and then you can solve that. That's not always the easiest approach. The mileage may vary here, but that's what we're going to do right now. Okay, so this is our equation system. Let's write it down once more in separate lines. So here we have, let's see, the first one is 2x1 minus 1c equals minus 2. The second one is 2x2c equals minus 1. And the third one is x1 minus 1 squared plus x2 squared equals 9. Let's get the constants on the right-hand side. And if you want to solve this for x1 here and x2 here, That seems like an easy thing to do because x1 only appears here, x2 only appears here. There's no x1 in this and no x2 in this line. Only thing we need to do is we need to divide by c. So at this point, we need to make a case distinction. So what we are going to do in the following is only valid if c is not 0. And we'll have to investigate that case separately later on. So let's say this is case 1. We are searching for solutions where c is not 0. If that's the case, we can solve for x1 and x2. So we first divide this by 2. We divide this by c, and then we add 1. And that means for x1, we get minus 1 over c plus 1. For x2, we just divide by 2c, so we get minus 1 over 2c. And we just keep the third equation as it is. And now we can substitute those here into the third equation. So that means what we get is, let's see, minus 1 over c plus 1 minus 1 squared plus minus 1 over 2c squared equals 9. Can simplify that a little. So that's 1 over c squared plus 1 over 4c squared equals 9. And let's solve this. So that means we have 5 over 4c squared. Yeah, 4 plus 1 over 4c squared equals 9. So what we get here is 5 equals 36 c squared. 9 times 4 is 36. So c squared is equal to 5 over 36. And that means c is either minus square root of 5 over 6 or plus square root of 5 over 6. Okay, so those are the two possible solutions for C. Both are non-zero, so both fit our case. And that means we get 2 possible candidate points. Let's start with the first one. So let's call it x star. X star corresponds to this value here, minus 5 over square root of 6. Remember x1 and x2, we solve for x1 and x2 up here. x1 is minus 1 over c plus 1, x2 is minus 1 over 2c. So that's minus 1 over c plus 1 and minus 1 over 2c in both cases. And now if we substitute that value here for c, what we get is, let's see, the square root of 5 over 6 plus 1. No, sorry, square root of, well, we of course is 6 over square root of 5 that way, plus 1. And here we have 6 over 2 square root of 5. So let's see, this is 1 over square root of 5. We can take that one out. And then we get 6 plus square root of 5. And the 2 cancels out with 2 times 3. So we're left with a 3 here. So that's our first point. And then the second point would correspond to this value here. So again, we have -1 over c plus 1 and -1 over 2c. And this time we get the negative values here. So we get -6 over square root of 5 plus 1, and we get -6 over 2 square root of 5. And that will be 1 over square root of 5. We take that one out again, and we get -6 plus the square root of 5 and 3. Minus 3, sorry. Okay, so those are the two candidate points that we have. And now, of course, the question is one of those actually a minimizer? Because remember, those are just candidate points. They don't have to be minimizers. But if there are minimizers, then those are the only possible candidates. And to find out which one of those might be a minimizer, we can just evaluate the function value. So what we want to do now is we want to find out about the value of f at x star and the value of f at x double star. And if we do this, I'm going to spare you the computations here. We should get, the first one is 15 plus 2 square root of 5 over square root of 5. And the second one is -15 plus 2 square root of 5 over square root of 5. Okay, so if you compare these, clearly that value of x double star is lower than f of x star, because the terms are almost the same. The only difference is here you have this term here, that's the same, and here you add 15 and here you subtract 15. So of course subtracting 15 will yield the better value. So this is the minimum. Okay, so that means x double star is the minimizer of f over c, or a minimizer, let's put it like that. We haven't excluded the possibility of a second minimizer yet. Remember, we still have the open case of c equals 0, right? We only dealt with the first case right now. And of course, we need to take care of the second case as well. Let's copy our equation system here. Then discuss the case 2. Looking for solutions where c is 0. Here's our equation system. Now, if c is 0, what that means is, well, this term here becomes 0. This term here becomes 0. So we are left with the equation system 0 equals -2. 0 equals -1, and x1 minus 1 squared plus x2 squared equals 9. And obviously 0 is neither -1 nor -2, right? So there is no solution to this equation system. And that means there is no solution with c equals 0. So we don't have to deal with that case any longer. Okay, and that finally settles it. The only minimizer of f over c is this point that we termed x double star here, this point here. That's our minimizer. And if you actually look at that function, see, I have taken the liberty of plotting that so that you can have a look at that. Unfortunately, I mixed up the notation here. So this here is actually our x double star, and this is our x1 star. So this is how that looks. Basically, the function f is a plane, and this here is our circle. Doesn't look that circular because of the scaling of the two axes here. So, but believe me, it is a circle. And if you minimize over that circle here, this here is the minimum. And remember that C only consists of that circle line, right? We don't have the interior, so it's not the disk. It's just that circle line that we minimize over, because we only consider points that have exactly a distance of 3 to this point here in the middle. Okay, that solves CA1. Any questions?
Yes, there are some questions. First of all, some students ask, wouldn't it be possible to eliminate the z by a suitable addition of the first two equations?
Of which equation?
So,
of the, oh yeah,
yes, we have a system of 3 equations, x1, x2, and z. So from the first, yeah.
So what you want to do is you want to scale those.
Yeah.
Basically, you want to multiply that by x2, and you want to multiply that by x1 minus 1, or the negative of that, and then add those two together. You could do that, but that doesn't mean you don't have to do a case distinction, because if you multiply a line by something, then that something, of course, cannot be 0. Otherwise, you just get rid of that line. Yeah, you lose the information. So if you multiply that by an expression that contains x's, then you need to make a case distinction based on whether that expression is 0 or not. But of course, that's also possible. You could go that way. It's just the case distinction looks different. You should get the same result, though.
Yes, and the second question. So in the constraint function h, why wouldn't we take the square? So basically, for the function h, so the function for the distance, it is it is the norm equal to 3. But why would we just take in the square? So it becomes x1 minus 1.
Why am I taking squares here instead of just leaving it as it is?
Yeah.
Yeah, so the reason basically is I get an expression like this instead of an expression that involves square roots. I could also have something like that, of course. And at least in my opinion, that pays off when I need to differentiate. So differentiating a function like this here with squares and no square roots, that yields expressions that become a little simpler than the function itself. Whereas if you differentiate square root expressions, you get something like 1 over 2 times that square root. So that it doesn't tend to get easier, right? So that's why I like to avoid square roots. But that, of course, that doesn't mean it's not possible to do that. You could just leave h as it is without squaring here and here, and use the original h, and that should yield the same result. Just yet your computations might be a little uglier than mine, but I haven't actually tried. Is that it? Any more questions?
Yes, some students ask, could we use the linear equation system approach with the inequality constraints as well? But personally, I don't really understand the questions.
Linear equation. So if you mean could we use Gaussian elimination, then the answer is no. So this is a non-linear equation system. There's no matrix that is associated to that. So you can't just use Gaussian elimination on that one due to the non-linearities. If that's not what you mean, then please just rephrase the question. Feel free to ask again.
Yeah, so for now, it is all the questions. So.
Okay, so let's have a look at A2. A2 actually is very similar to A1, so we basically go through much of the same stuff again. just a little more complicated this time, because the feasible region here, this F here, is defined by an inequality now. So here we have all x's whose norm is less or equal to 2. And that means all the x's who have a distance of less or equal, or at most 2 from the origin. So we have, again, we have the circle, but now we're taking the whole disk, right? So the circle line, including the disk inside, that's our F. Disk of radius 2, centered to the origin. And again, we want to minimize the function. That looks a little more difficult now, but not that much, yeah? So this is our F. So CA2, let's see. Here we go. So we have this feasible region F. Again, that's described as all x in the two-dimensional plane where the norm is less or equal to 2. And of course, you could again rewrite that as norm squared is less or equal to 2 squared. And again, I'm going to do that for the very same reason. I don't want to deal with square roots. But of course, you could do that. Yeah, it will yield the same results. So the norm of x squared is simply x1 squared plus x2 squared, and that's less or equal to 2 squared, which is 4. So this is basically the condition here. And we have the objective function x1, x2 that we want to minimize. And that is given as x1 plus 2x2 squared. So again, let's reformulate that so that it has the desired form that appears in the theorem. And that is, you want to minimize a function. That's already nice. So we have minimize x1 plus 2x2 squared. And we want to do that subject to possible equality constraints. We don't have any equality constraints here. And possible inequality constraints. That's what appears here. And we usually call those G. G of x1, x2. And again, we want to reformulate that in a way that there's a less or equal to 0. So the right-hand side is going to be 0. So basically, we take this condition here. We take the 4 to the left, and that's it. Yeah. So our function G is x1 squared plus x2 squared minus 4 is less or equal to 0. And now again, we want to find KKT points to have candidates for possible minimizers of the system. And again, we need to write down the KKT conditions for that. With inequality constraints, there's a little more conditions that we need to consider. Basically, what we get is, let's write down the full form here first. Again, we have the gradient of the objective f, plus we again have the Jacobian of G this time at x transposed times the vector of multipliers. We call those y for the inequality constraints. And again, there's one multiplier per inequality constraint. So in this case, there's only one inequality constraint, we get one multiplier. Right? And if you would have mixed conditions, so if there's also equality conditions, you would just add that term to the mix. So you also get plus Jacobian of H, X transposed, and another set of multipliers. Again, one per equality condition. And that will be 0. In this case, we don't have that function H, so this term just vanishes. Right? So this is, again, the Lagrange condition. Then we need feasibility. And feasibility basically means we need to make sure that the point satisfies G is less or equal to 0. And if there were equality constraints, also h is equal to 0. Again, not the case here, so we can forget about that. And now for the inequality constraints, we get a little more. Two more conditions. First is the multipliers for inequality constraints need to be non-negative. So the vector of multipliers is non-negative per component. And the so-called complementarity conditions, the multipliers transposed G is 0. Basically, what that means is you have this vector of multipliers here. You have this vector G of X here. If you have more than one condition, it's going to be a vector. And you do know that every entry in this multiplier vector is non-negative. And the G's by this condition here, those are all non-positive. So you have something positive times something negative. That means the result of every product here of two entries, this two, these two, and so on, that will always be negative. So you get a sum of negative entries or non-positive entries. And the condition that this is 0 can only be satisfied if each of those summands is 0, right? So that being 0 basically means same thing as first multiplier times first component of that function is 0, and second multiplier times the corresponding function is 0, and so on. So that's what the complementarity conditions say. So what that means is basically if the multiplier is not 0, then this expression has to be 0. So the inequality constraint has to be satisfied at equality, so that actually the right-hand side becomes 0, right? Or in other ways, if that is not satisfied at equality, then the multiplier has to be 0. And that's a condition that you need to play around with if you want to solve the resulting system. So let's apply that to the system at hand here. Again, what we need to do is we need to find the gradients of f. So look at f once again. So this was our f here. Let's copy that actually. Put it here maybe. So we still can have a look at it. So the gradient of f is simply given as 1 and 4x2. So not constant anymore, but also not that complicated. And the Jacobian of g so here's our g. Jacobian of that is given by 2x1 and 2x2. So that means the KKD conditions that we get are the following. Again, first condition is this one here, gradient of f plus Jacobian of g transpose times y. We only have one inequality condition, so there's only one real valued multiplier, only one y. So that means the first condition we get here is gradient that is 1 and 4x2 plus the Jacobian transposed, that is 2x1, 2x2 times a multiplier y equals 0. And again, that multiplier y, that's one real number, yeah? So that's the Lagrange condition. Then looking back at the KKT conditions here, and then we have this inequality condition here. So this one. So we get x1 squared plus x2 squared minus 4 is less or equal to 0. Then we also need non-negativity, and we need the complementarity conditions. Non-negativity is easy, just y greater or equal to 0. And for the complementarity conditions, we have x1 squared plus x2 squared minus 4. This is the g times the multiplier y is 0. So that's the KKT conditions for this optimization problem. Any questions so far before we try to solve that system?
I think there is one question. So would there be a difference if we have a greater or greater equal or strictly greater or equal condition? So.
Yes. So if you have a greater or equal to condition here, instead of less or equal to, you just reformulate that by multiplying this inequality by -1. Yeah, multiplying an inequality by a negative number turns the sign around. So that way you would turn that into a less or equal to condition. Basically, you get the negative of the left-hand side that way. So that does make a difference. For a strict less or strict greater than, things are much more complicated. Because you exclude the boundary, basically, of your region or part of that, depending on which conditions are strict and which are not. So basically, we're not going to discuss that question. That usually means there doesn't even have to be a local minimum, might not even exist. And that's why in practice, we're usually only talking about constraints that include the equality case. That includes the boundary, and usually the set that you're dealing with is compact or at least closed. And that gives you a guarantee that either the optimizer exists or it might be unbounded if it's not bounded. But at least you get existence in the usual case. Yeah, so we need to have the equality case included. Otherwise, we're just not dealing with that. You would need very different methods to do that. Any more questions? No, I presume that's a no. Okay, let's go on. We need to solve those conditions here. And again, one possible way of doing that would be to try and solve for the x1 and x2, and then substitute that somewhere. So let's first write out the actual inequality or equality system that we get. So those first two rows here, that will give us, let's say, 2x1 y equals -1. That's the first line here. And the second one would be, let's say that's an x2 here. We get 4 plus 2y equals 0, right? And then, of course, we'd have x1 squared plus x2 squared is less or equal to 4. We have y greater or equal to 0, and we have the complementarity condition -1 times 0 equals 0. And now what we usually do is we consider different cases for the multipliers here for the y. Namely, the cases that y may be 0 or non-zero, because if it's non-zero, then we can use this condition here to conclude that the constraint here must be fulfilled at equality. And this gives us another equation that we can use. Right? Remember, this is now only an inequality. So we can't really use that to solve a system, but we can turn it into an equation if we knew that the multiplier is not zero. So that's what we are basing our case distinction on. And that means the first easy case that we need to get out of the way first is the case where the multiplier might be zero. So let's first deal with the case that y might actually be zero. What happens in this case? Well, if you look at the equation system here, you can see that clearly you get an equation here in the first row that would then be 0 equals -1, and so on. Don't even have to write the rest. This already means there is no solution to that system. Right, so what we get is clearly a contradiction. That means there is no solution where y is 0. And that, of course, means we can concentrate on case 2. Y is not 0, and that specifically means y is strictly positive because it cannot be negative, right? Remember, this is one of the conditions here. Y is greater or equal to 0. So if it's not 0, it needs to be positive, strictly positive. And by the complementarity condition, that means if this is not 0, then this has to be 0. So x1 squared plus x2 squared is equal to 4. So in other words, this here is fulfilled with equality. And of course, these two still need to hold, so we copy those two. That's, let's see, 2x1y equals -1. And the other one was x2 4 plus 2y equals 0. And now let's see what we can learn from that. Now, this second equation here, that again has the nice property of a right-hand side of 0. So let's first look at that. If that is going to be 0, then either this factor or this factor needs to be strictly 0. Right? So that means either x2 is 0 or 4 plus 2y is 0. That latter would mean y is equal to -4/2, which is obviously negative. And that cannot be the case. Remember, y needs to be non-negative or even strictly positive in this case here. So we can exclude that case. And that means the only possible solution is x2 is 0. Right? So it means x2 must be 0. Now, if x2 is 0, let's look at this equation here. That means x1 squared plus 0 is 4. Or x1 squared is 4. And that, of course, implies x1 is either -2 or 2. No other possibilities. And finally, let's have a look at this equation here. 2x1y is -1. And let's see. If x1 would be +2, the positive solution, then that means this left-hand side would also be positive because y is positive. So it cannot be -1. So we can exclude that case, right? So if x1 is 2, that means 2x1y is positive. Remember, y is positive. And that cannot be equal to -1, right? Something positive can never be equal to -1. So we can exclude the case. And that means x1 necessarily has to be -2. And finally, that allows us to solve for y as well. So that means y is then -1 over 2x1. So -1 over 2 times -2. So that's 1 over 4. And you still have to do that to make sure that y actually is positive. Yeah, it could also be that this yields a negative value for y, and that means there's again a contradiction. So you wouldn't get a solution that way. So this is positive, which is nice. And that means we actually have a KKT point, and only one, right? There's only one possible candidate left. Only one KKT point here. And that is x1, x2, and y equals, so x1 is -2, x2 was 0, and y is 1 over 4. That's the only KKT point that is left. Now the question is, of course, again, is that a minimum? And in this case, we can answer that in the affirmative. That has to be a minimum because the function f assumes a minimum. And we know that because that set f, the feasible set, is compact. It's bounded and it's closed as f is compact. And the function f, the objective function, is continuous over f. And that means it does assume minimum and maximum over f. F assumes a minimum over f. So the only KKT point that we get must be a minimum. We don't have to do any more work to make sure that it actually is. It's the only possibility, and there must be at least one minimum. And that means our KKT point -2, 0 is a minimizer of f over the feasible region, capital F. Okay, so that solves A2. And as you can see, basically the difficulty here is in working with these inequality conditions, right? You get this inequality, you get this inequality, and you get this complementary slackness constraints here. And usually by doing case distinctions on the multipliers or other clever case distinctions, you use that condition here to turn part of the inequalities into equalities, and then collect enough equations that you can actually solve the equation system. And again, as you can see, through more or less clever use of the equations and the inequalities that you have, you can try to exclude solutions early, so that hopefully you only end up with one or a few solutions that you then have to check for all the equations. And of course, if you had more than just one condition, you have more multipliers and of course more cases to deal with. That will get a little more work, a little more complicated. You'll see examples of that in the homework part of this sheet. So there's ample opportunities to practice that. Questions?
Yes, there are some questions. So first of all, what happened if f wasn't compact?
So if f wasn't compact, basically there's two possibilities. It could be unbounded. And that could mean that the function f could also be unbounded. Things could work out nicely. You would get a minimum. Or it could happen that the function is unbounded, and as we're looking for a minimum, that would mean the limit is -infinity, or there is a direction where you can get to -infinity. That you wouldn't detect that. what would happen is you wouldn't get any KKT points, and then you have to try and find the direction where the function decreases indefinitely, so that you can find a direction where this is actually tending to minus infinity. The other possibility is that f might not be closed, it's not compact. And that's the reason exactly why we insist on these less or equal to or greater or equal to constraints, because with this equality included, that can't happen, right? So that guarantees closeness basically, and then we just need boundedness for everything to be compact, and we're good. And usually in practice you have some kind of boundedness. You're usually not interested in solutions that are very, very far away. So if there is no boundedness implied in the problem formulation, you can, in many cases, you can add one. If you can't, of course, you might be in trouble.
Another question, but it may be the same. So could you please explain once more why we know that this point has to be a minimum?
Well, basically that's due to KKT's theorem and the compactness. So KKT says if there is a minimizer, then it has to fulfill the KKT conditions. It has to be a KKT point. So in other words, only the KKT points are candidates for minima over the constraint set. And we only get one KKT point here, so that's only one possible candidate for a minimum, this one here. And now we know that f is compact and the function is continuous over f. And you know that theorem. It holds in the same way in one-dimensional analysis. A continuous function over a compact set assumes minima and maxima over that set. So there must be a minimum contained in the feasible region F, and also a maximum, but we're not looking for that. Right? So the only candidate we have found must be the actual minimum. That's the reasoning here. Needs to exist, and there's only one possible candidate, so that must be it.
So another little bit related question. So could you maybe repeat all conditions under which a KKT point give us for sure a minimum?
Can you repeat that question?
Could you maybe repeat all conditions under which a KKT point give us for sure a minimum? Yeah, it's something something similar to
basically
previous,
same answer.
yeah.
So the KKT point needs to fulfill the KKT conditions, and then we compute all the candidates, and usually the feasible set that we're talking about is going to be compact or at least closed. Yeah, so the function usually is continuous, so mostly you'll have those two conditions, and that means there is a minimum. So that means if you only get one candidate, that must be the minimum. If you get several candidates, then of course you'd have to find out which one of these is the actual minimum. And usually the easiest way to do this is what we did in problem 8.1. You just compute the function values and you take the one with the lowest function value. And of course, there might be several minimizers. So it can happen that more than one point yields the same function value. And that's the minimum function value. So the minimizer need not be unique. There may be more than one. But if you get more than one candidate point, you usually just have to compare the function values and see which ones are minimizers. Yeah, so it's usually a way to do that.
There is someone is typing, so could you just wait a little bit?
Sure.
So maybe the student asked the same question. So how would it differ if we were to take the maximum instead of the minimum? But I think you've already explained.
Yeah, but so basically the KKT conditions are formulated for minimization. And of course, you could easily reformulate that. You know that one from linear programming from your first semester, hopefully. If you have a function that you want to maximize, but you only know about minimization, what you do is you multiply the objective by -1 and you minimize. So you minimize the negative objective instead of maximizing the actual objective. Yeah, and you either just do that before you apply KKT theorem, or of course you can reformulate the theorem for maximization using that trick, if you'd rather do that. But keep in mind, the theorem as we wrote it down is the minimization version. So if you want to apply it as it is, you need to have a minimization problem. Any other questions?
Oh, yes, I think there is a last question. So how to deal with the multiple conditions? How do the KKT conditions change?
So basically, if you have more than one condition, the KKT conditions, the abstract KKT conditions do not change at all. Let's see. We wrote those down somewhere. Here they are, right? So this is the most general version. You may have more than one inequality condition, more than one equality condition. What happens basically is this function, these functions here, these functions G, that one here, that would then not be a real valued function, but instead a vector valued function. Yeah, so you could have something like x1 squared plus x2 squared minus 1, and let's say you might have another condition here, something like that. So you get a vector valued function instead of real valued function. And then you would get one multiplier per condition. So in that case, you would have two multipliers, right? Same thing for the equality constraints. H could also be a vector valued function, one line, one component per constraint, and you would have one multiplier per constraint. And as you can imagine, that might make things uncomfortable, more or less. Okay, as I said, there will be examples of that. We also see some examples for functions, for the optimization of functions over more than one condition. So let's delete that before it confuses someone. Basically, the conditions then look the same. The only difference is the Jacobian, of course, has different dimensions. So in this case, we got Jacobians with just one row. If you have more than one condition, you get one row per condition in the Jacobian. So this becomes a larger matrix. And instead of just a real number here, you get a vector of multipliers. Same thing here. And basically, that's all the difference there is. Of course, that means, especially if you're dealing with inequalities, that means these case distinctions here, those tend to get more complicated because you need to take all the possible multipliers into account. Yeah, and usually you do something like case 1, all the multipliers are 0. Case 2, one multiplier is non-zero and all the others are, and that could either be the first, the second, the third, or so on. And then see which of these different combinations actually yield feasible KKT points. Most of those cases you'll be able to exclude very quickly. In some cases, you'll get KKT points. In some cases, you have to do some more work to exclude those. Yeah, so the work multiplies quickly with the amount of conditions that you get. Any more questions?
No, at this point, there is no more questions. So.
Okay, wonderful. We'll be able to discuss this more next week if you want to. So central exercises next week will also deal with KKT points. So if there's any more questions arising, of course, you're welcome to ask then. And as always, or almost always, there's also tutorials. So this Thursday, there's no public holiday. That means tutorials will take place. And of course, you're invited to join us this Thursday from 2 to 5 and ask any questions you might have on this topic and all the other topics that we've discussed in the lecture. So feel free to ask about anything at all during the tutorials. So thanks a lot to Kyo for moderating the chat today. And I hope I'll see you on Thursday.